Thanks for watching my video. Today I'm going to express sine function as infinite product, and this is first proved by Euler. So we know sine A is equal to 2 sine A over 2 cos A over 2, which is multiple angle of sine, and sine of A is equal to 2 sine A over 2, and I don't want cos, so I want in terms of sine. So if I express in terms of sine, it is pi plus A over 2, because if you simplify this here, I can say pi over 2 plus A over 2. So we know sine 90 plus something angle is cos of that angle. So which is same thing. Now putting A over 2 or pi plus A over 2 for A. Okay, now if you put in place of A over 2 or pi over pi plus A over 2, and what we will get is, now if you put this, so if you put A over 2 in place of A, so I will get A over 2 is equal to 2 sine, in place of A, if it A over 2, they mean A over 2 square, and sine, in place of A over 2 mean 2 pi plus A over 2 square. Okay, now this is 1. Now if I put in place of A pi plus A over 2, pi plus A over 2, what I will get is 2 sine pi plus A over 2 square, and sine, in place of A, if I put pi plus A over 2, they mean and 2 3, so 3 pi plus A over 2 square. Now putting these two value in here, this in place of this you will keep this one, in place of this you will keep this one. So what we will get is sine of A is equal to, so here in this value we have 2, this also 2, 2, 2, 2 mean which is 2k. In place of this one, which is sine A over 2 square, let's arrange pi plus A over 2 square, sine 2 pi plus A over 2 square, sine 3 pi plus A over 2 square. Okay, now if you apply this successfully, so for, let's take for something, this will go on. Okay, now for, let's take 2 to the 7, so sine of it will be A over what will be this value here, it will be 2k. Okay, and sine pi plus A over 2k. If you see this, 2 square mean 4, so 1 2 3 4, 4 times having 2k mean it will be what, 8, so it will be having 8 terms, so this will go up to sine of and if you see here 2k mean 3, here it is end with 3, so if 7 mean it will end with 7, 7 pi plus A over 2k. Okay, now this will go on. So in general I can write as sine A is equal to 2 to the this 2 cube means 8, 8 minus 1 is 7. Here's a 2 square means 4, 4 minus 1 means 3. So in general I can write k minus 1 sine of A over k sine of pi plus A over k, okay, and sine of 2 pi plus A over k, and go on, and the last term will be sine of k minus 1 pi plus A over k. Okay, this is number 2. Let's name it equation. Okay, let's name it equation 1. Now if you take the last term of equation 2, this one, if I simplify that one, sine of k minus 1 pi plus A over k, and if I simplify this, and if you multiply k pi and divided by k min, it will be pi minus A over k. So we know sine of 180 minus something is sine of that pi over k. Okay, and the last factor, but one factor here, that means last second factor, it will be sine k minus 2 pi plus A over k, and if you simplify this again, you get is sine pi minus 2 pi minus A over k, which is sine of 2 pi minus A over k. Okay, now half and k plus 1, the half k plus 1 factor from the beginning is from the beginning here, and it will be sine of k pi over 2 plus A over k, because how come this one is that, let's say if I put k here, 2 k, okay, 2 square, k is 2 square, if I put 2 square, that means 4, 4. Okay, let me show you in the last. Let's simplify first this one. K will cancel, it will be sine pi over 2 plus A over k, so which will be cos A over k. This one, why? If I put k here, 2 square, let's put, okay, 2 square means 4, 4 pi over 2 plus A over 2 square, which means you will cancel, you will get 2 pi plus A over 2 square, which is, this one is just it here, this one. Okay, now next will be now from equation 1, combining the last term and first term, not first term, second term, second factor, last factor, this one, last factor, this one, last factor and second factor, because they are conjugate, because sine pi plus A over k, pi minus A over k. Okay, why conjugate? Mean in complex number, if this is a complex number, then conjugate will be minus of that one. So that's why I call it conjugate. Here plus, that's why here minus, so they are conjugate each other, and this conjugate each other, and so on. Okay, now if I combine that one, what we will get is sine of A is equal to 2 to the k minus 1, this one, and sine of A over k, because this one didn't have conjugate pair and sine of pi plus a over k. Since I combine second factor and last factor is sine pi minus a over k, and next term will be sine 2 pi plus a over k into sine, let me write here, sine what 2 pi minus a over k, and so on, and the last will be what, and the last will be this one, half k plus 1 factor cos a over k. Okay, now if I apply this one, sine this whole term is sine a plus sine b into sine a minus sine b, so which is sine a plus b sine a minus b. This in terms of sine is sine square a minus sine square b. So sine of a is equal to 2 to the k minus 1 sine of a over k, and let me put in front here sine cos a over k, and this can be expressed as this one, sine square a will be pi over k minus b will be sine square what a over k, and next term sine square 2 pi over k minus, let me write here, okay, sine square a over k, and this will go on. Okay, now let's say this is equation 2. Now if I divide both sides by dividing both sides by sine a over k. Now if I divide both sides by sine a over k and let a approaches to 0, which means a tends to 0, and taking the limit, let me continue here. Okay, now if I divide both sides by sine a over k, here will be, and taking the limit again, so let me simplify that first. Limit a tends to 0, here we get sine a over what, sine a over k, since we divided by sine a over k, and if this can be limit a tends to 0, I can write this by sine a over a into k a over k sine a over k, and this is same thing as this, because this a and this a will cancel, this and this will cancel, that means this two same thing. So we know limit a tends to 0 sine of a over a, from properties of limit, this limit will come here and will come here again, this will not go here because here is a, this is not a, so this is k. So we know limit a tends to 0 sine of a over a is 1 into this k into, and this also same thing, okay, like this, in this one, so just 1. So the left hand side, this one is just k. Okay, remember that one. So k is equal to 2 to the k minus 1, which is 2 to the k minus 1. Since I divide both sides by a over k, that this and this will cancel out each other, and we left is this only. And that something I want to say here. Since a tends to 0, okay, since a tends to 0, cos of 0 divided by k mean cos 0. Cos 0 is, we know, 1, so here will be 1. And here if you put a tends to 0, so if this is 0, 0 divided by this is k mean is 0, whole term is 0, so sine 0 is 0. Same thing here, also 0. So what we gain is this, this term and other term also. 2 to the k minus 1, what, sine square pi over k, sine square 2 pi over k, and so on. Let's name this as equation 3. Now dividing what, equation 2, okay, dividing equation 2 by 3. We get, now if I divide this, sine a divided by k mean sine a divided by k, and since I divided this and this one, this 2 to the k minus 1 and this one will cancel out, and no, this one will cancel out, we left is this one, okay, this one and this one will left, so which is sine a over k cos a over k and sine square pi over k. Now if I divide here sine square pi over k, that means this whole term will divide by sine square pi over k, and this and that will cancel, and 1 will give, so here it will give 1 minus this one, sine square a over k divided by sine square pi over k, okay, and this is one term, and this one is will come here, so this one will be 1 again, 1 minus sine square a over k divided by sine square 2 pi over k, and so on. Now this one I can get, if I shift there, k sine a over k cos a over k, 1 minus sine square a over k divided by sine square pi over k, and 1 minus sine square a over k divided by sine square 2 pi over k, and this will go on. Let's name this as equation 4. Now making k as infinitely large, that means k tends to 0 and not 0 infinity, k tends to infinity. Now when k tends to infinity, here let's simplify here. Limit k tends to infinity, k sine of a over k. This one I will simplify here. Limit k tends to infinity, sine a over k divided by 1 over k. I can say again, a over this k can be written like this. Now if you put infinity here, this one, since infinity means it is a large number, so this a is treated as a number, a small number. So small number divided by large number means it will be approximately 0, okay? Because here, let's say 1 divided by 100, which is a large number, which is 0.001, something and 1 something like that you will give. So when this the denominator k, when it tends to infinitely large, then and then in this becomes 0, so sine 0 is 0 and this also 0. So 0 by 0 form mean we need to use L'Hospital rule. So L'Hospital rule today you should take this to what, you should take this to as differentiation. If you take this to differentiation, okay, differentiation of sine is cos a over k, and I will take this, a is treated as constant over k square, and here also 1 over k square. This k square, this k square we cancel here, and so a is treated as constant, so it will come out here. So k tends to infinity cos of a over k, which is just a, because if this is large, if you put the value here, if it is large and the denominator become large, so it will approximately equal to 0. So cos 0 is 1, so this is 1. Okay, similarly for this cos, I have say here, if k is large, then mean it will approximately equal to 0, so cos 0 is 1. Okay, now here also same thing. If I take limit k tends to infinity, sine square a over k divided by sine square pi over k, and this square can be written as here. Okay, and since here k inverse, here also k inverse, and so I can write this again as k tends to infinity sine of a over k divided by 1 over k divided by sine pi over k divided by 1 over k whole square, and this one, and whole this term I saw here already, this one. Okay, so this returns to a, and a, this square means square over, and this whole term same thing like this, and it returns to pi square. And for second term, this also, if you take here, it returns to what, here second term also, if you take, it returns to a square over 2 pi square, which means 2 square also. Okay, now from this 4, from 4 I can say sine of a is equal to, since whole this term is what, here we get here a 1 minus, and this whole term is what, a square over pi square, a square over pi square, and 1 minus, and this whole term is this one, a square over 2 square pi square, and so on. I can write here 1 square, no harm. So in general, sine theta is equal to theta, I can write this as, this is product pi from r equal to 1 to infinity 1 minus theta square over r square pi square. So this is the proof.